I thought it was kind of tricky because I want to name it like Benzil something, and it's just it doesn't actually follow that kind of naming system because it's an ami with this CH2, so it makes it more like it's a phenyl, but not really. It's more like a benzyl group. But this is one of those things that you would have to go back, read, and make sure like you have the naming right because it's one of those things that'll trick you on. Because it took me like 15 minutes to figure out what else. Something else that I thought was important for you guys is to go back over your stereochemistry, so like E and Z and R and S. R and S is only dealing with chirality versus E and Z is talking about the bulkiness of your carbon atoms or chain of carbon atoms. So like how I have them drawn like this on the side is where the heaviness, like which way the heaviness went. So you can see like the Z version would be looking more like a cis something. It's not actually cis, it's just where the bulkiness of the chain is. And then the same thing goes for like where he would fall. So the reason that B was correct over C is because the numbering fit the name better than C.
I mean, yeah, that one is trans, the other one is C. E, right? Because that one has coefficients, right. So it's not easy confirmation.
Exactly. And the next one, you kind of keep going back in this pattern. It's just like I thought it was important for everybody to practice the easy thing. Because if you have heavy stuff here, that's going to give you Z. If both heavy things are like up, this is that's like E, and then both heavy things up gives you Z. It's like the opposite of what you want it to be, because like when I think of trans, I think the letter Z. I don't think so. I haven't come across any that work because you get like
there's a couple for like aromatic things like Halloween.
Yeah, like that's what I'm saying. Like some parts of the book I didn't go all the way through because I know you learned this. Like that's the first part of the aromatic chapter.
Yeah, Halloween's theory.
Right. So like things that should be parents or ingrained in you, go back over, try your flashcards, do it. I'm trying to keep from being redundant in the child through each and every one, so you know what it is. Okay, so this comes back to your Lewis structures, which also comes from your orbital one, or killing one. So you just need to understand like how oxidation works with this, or like where your electrons actually are. So I know it's small and hard to see, but it's actually yeah, so it would be this is a 3 electron instead of 2. And then you have your extra electrons on the outside, so that constitutes as a full octet for both because they're sharing the 2. Yeah, it's like how it's printed is really small, so it's all 3. But even if you didn't know it was 3 there, and you went through and counted the rest of them, the rest of the electrons don't add up, or it's too many, or they're not connected right. Like you would never see this. So 6 pi electrons. This goes back to our aromaticity. So you want to go back, read over your frost cycles. What constitutes something that's aromatic? So you need to know your numbers: 2, 6, 10, 14. It was like that. 4n plus 2. Exactly. 4n plus 2. Even though it's not actually, that's what we had a lot of problems with. it's not actually 4n plus 2 is something, it's any integer that you put in for n, so like 4 times 1 plus 2 at any point will give you 6, not that you actually had 6 of something. You know what I mean? Okay. The carbocation stuff, this is definitely like something that you did in Chem 1, but it's the one that, the strongest one is the one that you can easily stabilize. So by that it means like with resonance, moving this double bond around circle, where do you find the most stability? Like with the rest of them, the double bond is too far away or the direction that it would move in when constitute a resonance structure.
Right.
And the lower position is a little bit stable cracks.
The what?
A little position.
Yeah, exactly. So yes, okay, so this is another still resonance question. It's just asking, can you figure out like which way the bonds will move? So here, what you have is your oxygen has the negative sign. So once you pull the negative sign down, make the double bond again, the rest of the bonds have to move around the circle as well. So it's just, can you see what's going to happen in all of that? So the same kind of question, we come back down to, can you find the air intensity? So one of the big things with that chapter was, when does nitrogen contribute its electrons? And it's only in times when it has a hydrogen that could put its electrons back. Like, because of resonance, it would be able to be aromatic. So like, so same question. So this is still another question about resonance and why is this anillium or ion stronger than NH4 used to do the resonance and like how it can use the ring itself to satisfy this that ion. Okay. So your weakest acids or strongest acids, whatever you want to call them. It depends on what you're looking for. Like, depends on what this question specifically asks you. But since we know that this is the normal way that you find your acid, so anything that deviates from that will be weaker or stronger. So we have this strong, this donating group here, which takes away from the acidity of it. So that will make this the weakest acid in comparison to what it normally sounds like, and these are strong withdrawing groups. So it's already pulling the electrons away from the acid. Right.
When it loses the hydrogen, the negative charge becomes stabilized by the electron withdrawing.
So like, imagine you and your friends locked arms and stuff versus like you by yourself trying to stand against something. You know what I mean? So like, so imagine like I'm pulling on your shirt and you're trying to stand here still. You know what I mean? So, or like if I'm pushing you and then you're still trying to just be still. I don't know if that's a good analogy for this, but that's like how I'm thinking about it. Do you have something better? Somebody else can explain it differently.
So if there's like electron donating group, then there's more electrons being donated into the center.
Right, towards the acid.
And that kind of keeps the hydrogens stuck on this.
Right, it's
Or
like
no, they're more stable so that.
right. Because
You think I usually think of the conjugate base. Like I don't even look at the acid. I just look at if it wants the 9, the negative charge. If it has an electron withdrawing, it can resonance it back into the it has a resonant form that includes the withdrawing.
so what you need to do is go back and look at what makes a strong acid and a strong base. So you have, if it's a strong acid, it usually has a weak conjugate. You know what I mean? So for it to be, these would be stronger acids because of the base that there would be weak acids but strong bases, you know what I mean?
Yeah.
So that opposite part, like you said, the conjugate base is what determines how strong the acid is. So you have your axial and equatorial chair conformation. I always get it drawn, these things, along with those other things that come along with when you do your Gauss algebra, and they look like these crazy triangles put together. Basically, what you need to remember from here is equatorial position is the strongest one. If you want both of them in equatorial position. This next question is like important because this one is when you think about this kind of thing. If you have an enantiomer, so we mean mirror images of each other, then nothing about them is really all that different. It's like having two different drugs. One just fits better than the other for certain things. So what you have to do is like, okay, even if I boiled these, melted them, or checked the density of these two things, they're the exact same. Just one's the left hand, one's right hand. So what would be difficult to measure about these two things? What would make them different? So it was the strength of interaction with the membrane protein. So, like I just said, the drugs actually latch on doing their job versus not being able to.
That leads to
Yeah.
even anomers?
Yeah, all the nanomers because they're the same. So basically, ask yourself what's the difference between your left hand and your right hand. Absolutely nothing. Except one's left, one's right. Okay, and this is the same kind of question, right? Can you identify enantiomers, diastomers? There's still one with each. There's mesocompounds, but it was like H something. I could not remember it for the life of me. Somebody else will know. But there is a whole list of things in this. I know I can't want to, so you need to go back, refresh yourself on chirality, stuff like that. No, diastamers, no matter what you do, you can never get them to mirror each other. So like imagine doing this with your hands. Like you can't, no matter how you turn them, they won't match unless you flip them.
They would have one chiral center that is R, and the other one is S. Just one, right? Yeah, we have a large molecule. If a single one is R and a single one is S, but the rest is the same, those are diastereomers.
So they'll never cross. They look the same, but they'll never be the same. This is also the same kind of question. pretty much all through here. Being able to draw your resident structures. I know you guys did this, but I don't remember it being a large part of the class. But, yes, human projects and close. So, because that's where only one person like ever asked me about it this semester. But what you want to do is you want distance between like two different groups. So like kind of the C is for your OH here. This is too close together. And then over here it's also still just as close together versus here where it's across from each other. It doesn't mind, like it won't mind it if two of the OHs are next to each other.
Now, if we're comparing like staggered versus the first ones, will the staggered ones, no matter how they're oriented, be more like stable than the eclipse?
Right,
Is
yeah.
that right?
Yeah. But this is not something I would stress myself about because I think this is literally the only question in the book like this, and that's why I picked this page out. Yeah, but we're back to our SNR. There's a girl who does it on YouTube who's really good. Like she makes it as simple as you can about like flipping it. So I would go to school to current centers, you know. Like questions you guys should think about. So like here I'm just writing down what S and R meant. Superimposable, non-superimposable. Like when you get to your test, some people I like to draw everything that's like a term or something that I could possibly forget between now and then. So this is so one of those, like, you understand what these things look like and what does it mean for it to look like that. So that's yours.
What was that first?
This one?
Yes.
Oh, okay. So which you need to first? Okay, which of these is right? Okay, so which of them would be more like enantiomers, where their melting points would be the same versus not? So when you start adding isomers to something, like basically enantiomers are isomers of each other. So when you go to like the racemic form or the mesoform, or you're getting out of this enantiomeric form of it, then it becomes like not the same. The boiling point is not the same, density is not the same, and melting point. So that was what that question that we did on the other page was referring to. Post and stuff.
Square.
Okay.
And then just like the OHs versus.
I think that's what I see.
Like just.
They're the, oh,
Did that for one.
I remember what I was just against. Okay. They're the only ones that could actually be transverses from each other. Because it's like when you're looking at these, this, right, they're missing parts. Like, you know hydrogen is here, but the hydrogen doesn't really give it that transversus look. Versus this is like on a shape. This one, the double bond is too close to the end. And then this one in the middle, there's too many double bonds. Exactly. this is like where we got beyond, okay, do you understand the basics of how to form reactions to actually doing the reactions? So it's asking you, which reaction would you start with to get to the product? So if you start with BR, what do you guys know that like usually you mix BR with and something starts happening? Double bonds. Has a specific reaction. He has a name. Starts with a G. Green. So yeah, you want to make sure that you go back, brush up over those. That was like I think chapters like 16. No, not 16. It was like 17 and 18, and then towards the end. So basically, yeah, they want you to see that you start here with bromine. The bromine can be plucked off on this double bond because these two things look almost alike, and then this OCH3 comes from here. So basically, how I start going through picking at this stuff. So yeah, basically how I start going picking at these things is what looks the most like this? Because going through this whole book, they're not picking things that look completely abstract. It's like you can if you can pull it apart, you'll see like they all came from the same place, kind of thing. So just like when you get down to it could be this or could be that, go to which one does this look like? So which of these anions would be most good towards methyl iodide in an ethanol solution? Basically, how the sulfur doesn't like making double bonds. It doesn't want to have double bonds. Adding a OH to kind of any of this, because these oxygens here have a charge and everything. Right. So this is here where you start working with your green earth stuff and going back to your aromaticity. But this was like one of the first problems that they showed you in the beginning of the book, and in the beginning of this chapter, and they were showing you how, if something is aromatic, that it will not go through a reaction. Like you would have to put a whole bunch of stuff in there, like salt it up, heat it up, and then hope for the best. Here they're showing you like even still you have to think about stuff like that. So with this one, again, even if you don't know exactly what these products do, well, these reactants and what products they're formed, just look at like how do you think they'll break apart. So if you can find at least two of them, okay, you know that you're going to have one with the OH part, because once this breaks, and then you're going to need to fill this carbon back in. So you have your OCH3 here. And you know, since they originally already were not only single planes, that the OCH3 was stuck up, so you would have two arms up. And then your two down. And it gives both of those carbons the stereochemistry. So, and then another thing about this test is when you see double bonds hanging out close to the end of something, like it's how I have drawn out here, like double bond on the end, double bond on the end, it's generally not that answer because you don't see stuff like this unless you're doing like biochemistry. If this is just like organic right now, then things like this won't actually happen. And then this. So then the bonding here, which is a little little bit weird. So it works out that when you're reading what you have come together, that this is the only plausible answer. So you have to, like, when you're reading these questions, you need to read, and this is why naming is important, and understand what the name is saying, along with being able to deduce, okay, so I have a base covenant. What kind of reaction is that? More than likely probably going to be like a nuclear valve coming in, moving something, kicking it out. This is again the same question, just like Halewich, because it was simple, and they use it pretty much through this whole book. So again, back to my solution. If it's got something, like if it just looks funny for me to draw it, it's probably not that one. Going back to this, it's back to residence and then BR being a good maneuver.
But I have a question about the one before. If it was a different base, if it was like a bulky base, that could be one of the answers, right? It's a secondary card. If you use like turn it outside, you'll push it to the
Right, and they do use one like later on, in, like even if you go through the pieces I plucked out, they use it like one time.
Yeah.
Usually it's gonna be chlorine, it's gonna be OH, water. Like it's not something heavy and bulky. Like those are kind of like class questions, and I guess they can't say they can do anything like that. But so I would pretty much looking at how the test goes is pretty straightforward. Like what they show you is pretty much what they mean. It's just can you deduce all the information that you've been learning this whole semester. And over here, they have questions about deuterium. So that's like H, like 2 plus instead of just regular H plus. And it's just asking, where would it come in and attack? So they have these H's here labeled, and basically it comes down to which one is not terminal and which one has like a carbon that can donate a hydrogen. Like when you see like this CH can donate a hydrogen back even if the deuterium didn't work out. And the rest of them are kind of locked in there on the end of carbon. So when they're on the end, they never want to come in there. Any questions about anything so far? Like any you feel like you should focus on? Am I hitting the point that you want to get at?
Yeah, I'm just worried about synthesis. Like, I don't remember much of this stuff. I feel like I have to really sense that I'm forgetting.
Well, back to the flashcard situation.
Yeah.
Just go home and
It's
like.
just like engagements and like whenever we specifically name a specific kind of reaction that happens.
Yeah.
It's like those two things.
Yeah. Well, okay, so not until the back of the book do they get specific, like going back to aldol reactions, maleic reactions, and all that stuff. But that's basically just adding water to something. Like a lot of it is just adding water. When they're using their lithium, and the BH4 and stuff, you're gonna want to go back to your book. But I think it's in the same chapter with the aldehydes and ketones, like that's where much of the synthesis started happening. And then they went into the Diels alder. Yes, that stuff. And it just kept going on and on and on. But once you realize like a lot of them do the same thing, it works out. I think what the best part would be like in the back of the book, not back of the book, the back of the chapters, they have like all the reactions laid out for you.
Yeah.
So like go write those down. Write down like what chapter they came from so that way you know what reactions to go with. Makes sense. Because that does become like a big part of the test, but later. So. So this is just like one of those questions, and I what you're reading. Like if something doesn't make sense, go through and scratch it out. Still, have to grab it right now. Which alcohol would be dehydrated the fastest? And it's always the one, it's usually the one, if it's one sticking straight up, it's always that one. It's like a sore thumb. Or, because when they're mixed into the equations, they're a little bit harder to detect, so that's why I was like, which one out of A and C? But then this carbon that this alcohol is attached to doesn't have hydrogen to join it and stabilize it. So that's why the A was the answer for this one, was the hydroxyl alcohol. And then there will have to be something that can come in and stabilize the rest of the reaction.
Why not the last one, the primary alcohol? Why would that work?
This?
The last one,
Because the same reason that B1 doesn't lead to stability, and then it's like it's on the end. It like when it looks like it's a part of it, it's usually a part of it. You know what I mean? Versus it being a piece of it.
like the drug theory?
Yes. Yes. So even though they are all technically hydroxy groups, out of these four, A and C look like they're the most ready to leave because they're sticking up at the top of it. And then what you have to come back and realize was, okay, what role do the hydrogens play in resonance stabilization? So like if you had something that was creating, that was, so basically you would have.
If I look at the carbon patterns, then that would make sense, right?
Right.
Because most of the charge on a tertiary carbon is more stable than on the primary is the very end.
Exactly. So like when these, it'll be like, oh, hydrolysis thing happening right now, something creating water, and then waiting for something to come back in and attack it. These are pretty much, these are where your synthesis questions come in, but right now we're just still kind of basic like acid base or water company. So yeah, they're basically still asking you the same type of question as it was on this page. So which alcohol would leave first, but this one is going back to okay. So which one would be hydrolyzed first on this side? So this was one of those tricky questions because it went from being a square. So it goes from just being a square to this pentane, cyclopentane. And that's because you have so many carbons sticking off here that the molecule can reshape itself and form the pentose to be more stabilized in the cyclo form. So when it says E2 elimination, that means you got something coming in, a couple things going out. Well, with that, basically, when you looked at all the choices that they have, I know I'm a word, but like all the choices that they ended up having down here, none of them looked like something coming in, something going out, except the first one. Like it was just like the most smoothly flowing answer. So sometimes it is like that simple. And these questions all came like out of the practice part, so it's not like they gave me the answer like in the beginning of the section. So I'm pretty sure this is what the test is gonna look like, because I never actually saw this test, because it didn't exist when I took this class. Go back to your system trans and what looks the most like the thing that you already have. What looks the most like the thing that you already have? Sorry. So this goes back to when you like first started learning about how to use bromine, and when you're about to learn how to use your Brynnae reaction, and like how it could do like this. It would, if it's in excess, the bromine can come attach itself to the ring, and then the excess part would create a longer strip, so it would just break it apart.
So is that like an essence though?
I don't think you could treat it like that because it's in excess. So you have to just like show that you did it twice or more times, because it would just, like, imagine you have something like precipitating out and it would just like all be happening at one time. Like, you can't show it all at once, but it's all happening. I don't know how to explain this to you. Like, you can't just show an SN2 and then expect me to know that you have two parts more than one time. Like, because there's already.
Yeah, it's just two and then another bromine comes in and
Right.
goes to the anion.
Right. So like when I did this, we just would show.
Does it say excess at the very end?
Yes, HBr with excess.
Oh.
Yeah. So then, like when you look at the rest of these, some of the answers get a little bit shorter, or like here, they just don't go with what you already have, because this is basically what you have here.
And how does the bromine replace the OH at the very end of the allergy?
Because it's in excess. So like there's so much of it that the OH is becoming water, like in solution.
Oh, it'll protonate and then come out.
Right. So they're all like, that's how you get a solid at the bottom and then liquid still at the top. So like this is showing you have two things floating at the bottom.
Yeah.
Did y'all take the lab yet? Oh, okay. This will make so much more sense.
How was the lab?
I loved Porto. I didn't think it was, I mean, it's a long, here it's a long time, so I don't know, you might have to sacrifice your weekends for it, but.
They made it look shorter though.
Really?
It's usually 7 hours, right?
Yeah,
It
it's,
looks like 3.5.
also they're letting you do it like twice a week.
It's still like if you take the class, it says 7 hours, and then you go there and it's like 3 hours. Yeah.
Because I'm like, I remember my friend, she was in there for 6 hours every Saturday. I'm just like, yeah, so back to predicting products, you're using your halogenation rules. So this will be the same thing as if you had like a PR come in, and it's always gonna go to the more substituted carbon. Anywhere else, that was kind of wild.
Unless we have a peroxide, right?
Maybe more specific rules. I don't know.
I don't know, it's just like I remember from number 1, if you have the bromination under peroxide, you have an acceleration.
Yeah, but they haven't done any like sequential steps, you know what I mean?
Yeah.
So it's like the one thing and then that's it. Like,
It But it's a single step.
Yeah, this is just single steps. Okay, I haven't seen anything in here that's like, to show me A, B, C, and D of the reaction. This again is one of those other deuterium questions.
Yeah. See that peroxide? That's what I'm trying to say.
Where is the peroxide?
H2O2, hydrogen peroxide, on the second step, below the deuterium.
Below the deuterium. Okay, yeah, this is a halogenation. Okay, this was what I was talking about before. Okay. This is a different type of problem because deuterium acts differently. So yeah, no. So this is B2B6 and H2O2 and OH. I'm like, okay. We have your deuterium, and then your OH should just come in. And then the rest of it turns into water. What's the question?
No, yeah, it was that I was saying, like the deuterium gets added into the less specific carbon because of the peroxide. It's part of the mechanism, I think. That, like you have a radical addition of the hydrogen into the
I'm not 100% sure on that because deuterium and then the tritium, they all follow different rules than like a halogen would.
How does this reaction
So we have this here. These two are the same thing, relatively. Your D6 is what that extra halogen is. Okay. So the deuterium was going to add here to the more substituted hydrogen, carbon. Because we saw that back when I was showing you, okay, which it's not going to add to the terminal carbon earlier, and then it's not going to add to somewhere where the carbon has something to it to stabilize. So the resubstituted, so that marks off this one and that one. So this is now satisfied. Your OH from here, this is the only place it could go. It would only come up. It wouldn't push on the hydrogen to be face down with the CH3. So it's kind of like just understanding like which way the bulkiness of the reaction would have went because now you have this H has always been here and it had no stereochemistry before. So now you've lost a double bond. So the reaction is going up.
because there's peroxide that causes OH to be at a less substitute, and that's why the deuterium is on more substitute.
Well, the deuterium it has a water part, so it happens first.
That's it.
One B2 D6 2. So the deuterium reaction is going first, and then once that's there, that's how you got rid of the double bond. So now you have to go through with the second reaction.
What would the deuterium by itself go towards the
More.
substitute if it usually goes to the less substitute?
No, it goes to the more. I wrote the less substituted because that's where the second part was going to.
Right, but in a normal reaction without peroxide, hydrogen, is it just different than hydrogen? Just like it doesn't.
I think this is because the deuterium acts like a blocking thing. You know how when you had to learn about blocking reagents for synthesis problems. So I mean, because it has weight to it more so than like a normal hydrogen would, that it goes against the rules. That's what I'm saying. You have to actually read about it because they never actually said it in Ordo 2. I think it might have came out of Ordo 1 somewhere.
Like, no, you never really mentioned it, but they mentioned it as like the deuterium will randomly associate and disassociate from a molecule in relation
Well, but see, I don't think that this one is going with the same rules because it's not random. It's like this happens first and then this is going to happen second. So this is just one of those problems. But it does have the enantiomer, so basically this is going to be flipped too. So it's going to be this way and it's going to be the other way.
Isn't the enantiomer isn't just the flip of the actual like a vertical flip?
Yes, actually, you're right. No, yeah. So up and down. So it's still okay. So the OH is still going to go to the least. Well, it's not even least substituted anymore. It's like it's a nucleophile at this point, and then the carbon had a plus sign. So it's the only place it could go.
I understand the theory, but I don't think I will.
That's what I'm saying. I was like, it was these two questions. I'm like, if you could
I mean,
answer.
if I saw that, I would have like saw you the website, I would have straight out went down to my coffee cup. So I would either got an A or D. I wouldn't have known. I guess antimarcomic coagulation with peroxide is also an anti-addition, so the opposite side from the methyl. So I would know with A based on that logic. I wouldn't have like even messed with the theory at all.
Okay. So what we just went, okay.
Yeah.
So B, we see that B is wrong. And we see that D is wrong. Because if B is wrong, D is wrong for the same reason.
Yeah.
So, not B, it's D, I meant C. Oh, I'm so sorry. So if B is wrong, C is wrong. D.
The other one is just like the stereochemistry of the peroxide reaction.
Right. That's what I was saying. I'm like, an enantiomer of that thing. But that would just be it flipped upside down.
I feel like if you have peroxide, you can only have it untied to the methyl group. I'm not sure why, but I know it's a rule that heard it in Virgo. Like if I had what was it? Hydroboration. It's hydroboration oxidation. That's also hydroxylation, right?
Yeah, hydroxylation. This is like a super oxide type of thing. I think the thing that makes this one a little bit different is just because it's the hydrogen peroxide plus the salt, the hydroxide, sodium hydroxide. So it's turning into water just as quickly. So I don't think it's like as strong as if it was like just H2.
It's a radical mechanism though. If you have hydroxide, you have OH radicals that will just like line on every position with the double bond. It's the same. You just keep going. It doesn't really matter. Like, I think if you go with like the rules for atomic combinations, if you know which one is anti and which one is syn, then you can figure out which one is the right answer.
Well, so I don't know. I was asking one of the other students. I'm like, okay, well, what is this? So I was just like, okay, I got the explanation, and I was just kind of like, whatever. This comes back to like resonance stabilization. However, which ones are, which ones aren't. So this one is just getting down to things that it couldn't be, like the hydroxy group was just put in all the wrong places, and then there was no reason to move the methyl group from its original location. They changed the whole reaction, so that's why that part was wrong.
But the initial reaction, like not here.
You let me get through the whole explanation. Okay.
Yeah.
So you have your CH2, CH3.
Oh,
So like what they did for part D was they moved the whole methyl group. So this is no longer even the same reactant that it is. Like this could not happen. But they were right in the sense that your OH was going to go to the more substituted carbon. Well, it's not even that it's more substituted anymore. It was that it's lost its extra double bond. So please do not be another one of those questions. So yeah, so this is the same question as whatever we were just on. Okay. So like, I think you're right from beforehand. But I think it's because the B2, like the H is not deuterium. And that's why I'm thinking like, because it's a deuterium.
what is a B?
I think it's just the carrier. It's just carrying the hydrogens.
So it's like reducing it? It's like a reducing agent?
The hydrogens would be reducing the thing. Yeah. Yeah, it would be like having Mg with the MgBr.
Oh,
Like it's just all carrying the thing. So like with this one, since there's no deuterium, your hydroxide could go immediately to your
yeah.
more substitute carbon. So I think it has something to do with the deuterium that changes the answer because it's still the same reactants as before.
But it's the same answer though. It's the same mechanism. You have an anti-isolation
No.
and that's the drug.
This one, your hydrogen is not deuterium, so like they're not on the same place because you remember the hydroxide was on, it would have been on the other. Our hydroxide was here, and our D was here.
I don't know. It's fine.
This is going back to like what I was talking about earlier, where this is like towards the end of your class that you just said. They had a blocking steps and what withdrawing groups did to your reactions and how you'd be able to use like several sets of reactants to make a synthesis problem to get to a final answer. So this one comes down to even if you didn't know exactly what HCl was going to do, you would always pick the answer that it looks the most like. For the rest of them, they just started putting the chlorine in places that it just couldn't be, and then they started changing the molecule. Like, why would you shift everything down? That's not necessary because it had hydrogen that could be removed. Instead, the chlorine could come in. And
It's like the most stable formation.
right. They're just asking what kind of reaction this was, and basically it came down to the hydration. So, because all you added was the OH here, you wouldn't necessarily have hydroxide or a hydrogen or hydronium ion just hanging out in solution, but water is always present. And then you have to go back and then study. This was one of your, to make a ketone problem. So you go back to the ketone and aldehyde to figure out how did you get here? Why would it have been this? Why didn't it go over here? And this They don't usually make two unless it says something is like in excess. For sure you guys do acetaldehydes. Acetal formation, like from acetaldehyde. I was watching Hanukkah yesterday and he was saying it wrong and I was like stuck in my head. But yeah, so it's acetal formation from like hemiacetal to acetal, hemiketal to ketones, and this is from when this was also during the whole aldehyde ketone thing. Basically, the other part that it came down to was, did you know what these two, if you knew what these two things were, which is what I drew over here in the corner, then you could pick which one it looked the most like. Like most people would want to pick this one because this is the one that's in the book. But it's actually this one because it's the cyclopentano. And then it's like, did you know what pentano meant? If you did, then you would have realized that you were missing a part of this one. Okay. Here's like a list of your reactions. So like probably that, because there was during your diazoxide, which did your 1,2 additions and 1,4 additions, which ones were more stable. So it wasn't exact. It wasn't diazoxide. It was like it's a set of 3, like sigma reactions, electrocyclic reactions. So like this is where that would be. Yeah, what time it is?
4:07.
4:07. Okay. No, I just wanted to give y'all a break, like if you want to get water or do something for a few minutes. So this one will then again be going back, learning what your reactions were. Like I kept writing it down, like learn the reactions. You just have to go back and learn them because that's the only way that you would know what the products would be. Because I know for a lot of your classes they would just ask you, give me the products. Like don't do the mechanism, just show me products. I'm like, that's not how I learned it, so I had to adjust. But yeah, so you would just go back and do that.
What is the
I don't even know, because I didn't see this. I never actually saw this in your book, but it was. I drew it out here, so it's
like Velvet? What does it say? TSOH?
TFOH is up there.
Okay.
C6,
It's like a really strong plate.
C6H6, and then heat.
And C? No, that's C6H6.
Yeah, I don't remember. I don't remember seeing this one specifically in your book, so I don't know. They just pulled it. I don't know what. What happened with this one was this is what our top part is. This I think is just carrying along the reaction. So if we know this is what it is plus that, then we just saw that on this other side here. So we knew what the reaction was going to be, or what it could have led to.
So the one that's below, it has to be like some sort of dry acid, right? So that's like any acetone?
I mean, it's just, yeah, it's probably like, you said the dry acid because it's acetyl formation. Good luck, Brynnae. This was another one of those where you use H2S with 4 as your blocking group. well, you add this and then use that as your bond food to get the rest of the reaction. So it's just, again, I get to a point like, because you can't like, it's unlikely or unrealistic to ask someone to remember every single reaction. So like with this kind of test, when they give you plausible answers, and then they gave you what it's already going to look like. If it looks nothing similar to what you already have, it's not that.
So that's also an instance, right? You have, if it says alcohol to a ketone, uniform and acetone. That's OR. I don't see the part below it. What's the second? Yeah. Okay. So you like
Yeah, because they're both on the same carbon, so
Yeah.
they're OR, yes.
Yeah.
I think it continues on like this for a while. This is just like a sucrose, so like anytime you see something that looks like this, it's a 1,4 beta linkage. So that's
It's
how.
like early century.
Right. I had this question I had to test this morning. So like, regardless of what you're doing, that's always the answer.
Yeah.
Reaction. Okay, so at this point, you should know how to look out what our nature product says. This should not have changed much. So whatever they were adding
Oh,
or
you can have that on my last test.
yeah.
Yeah.
So it should
It's all methane, right? I don't know, it's just the inactive one. Only the one that is next to the oxygen.
Mm-hmm.
Yeah.
Okay. So I remember there was lithium and H4.
Yeah, that's our reason.
Okay. There you go. And then we understand
What is the what does the double bond though get reduced as well?
Okay, so this was one of the, because it says ether on the bottom of it as well. So I was like, this is one of those weird ones where this double bond is actually the answer. Like the weird double bond situation. Because I think it reduced, because this is how it already looked when it started
Yeah.
here. So it reduced your oxygen to have H here. So any other answer
Yeah.
that wasn't
If it wasn't terminal, then it would get reduced as well, right?
right, yeah. If it didn't already or initially look like this, it would have also changed. But since this was just a reduction, you see you have your ketone group. It's been reduced to an alcohol.
Yeah.
This comes back down to knowing your reactions. I don't know exactly. I don't think you had any BB4 on your list, so I would need to.
You do what?
Any BB4.
Yeah, soluble hydrate. It would be more of inferior hydrate.
Okay. Yeah, is it
What is the answer now?
B? If that's the answer.
Oh yeah. Okay. Why?
Okay, I can understand why now because the boral part is just carrying the deuterium, like in the earlier part we were looking at.
Yeah. But why is ethanol as solvent? You know that?
Solvent for which one?
For NABD4. It's in ethanol.
And because I think it's because it's in an aqueous workup and an aqueous workup. So in solution, it's probably because in some labs, like ethanol is the only thing that will keep it stable. You have to use something that's cold and that won't react.
Oh, okay.
That's just like that's one of those things you just learn in lab. You wouldn't remember it from class.
I see.
this is just another green yard. Here. Okay, so they're just asking how the green yard come in and then take this off so that there's like that. So the creation of your aldehyde group.
CHM?
It's just asking like if you had which
Oh,
one
yeah.
wouldn't produce the alcohol with?
Oh, like a third retail sort of thing.
Yeah.
Oh, I see.
And which would be a reasonable and for the mechanism. So just basically at what point would this come together? So you can see with the OH, so your water came in the bags here, and then your extra electrons went at the top, and your hydrogen came in the tank. So this would be like the midway point before the reaction completed with CH3 OH.
Yeah, before the catalyst.
Mhm.
Catalyst. Right?
Yeah. Okay, and then this is just asking for most reactive wood aqueous ammonia. So the reason that because your leaving group, your anhydride would break apart, and then this would form your ether ester. So it's just asking about reactivity with other reagents.
What happens to the ketone of the acid chloride?
I don't think anything happens because it's like your R, like your C ketone group with the R, and the chlorine is just acting as a leaving group. Like it would never be left like that. So either it would turn into aldehyde or another like.
Glucose ammonia? What is the function of glucose ammonia?
It would be reducing agent because it's NH4 plus.
Huh.
So it would probably be what donated a hydrogen here.
Oh, the ketone is reduced by it.
Mhm.
Yes, it does. Right. That's what I thought. I mean, that's what it is.
It would turn it into the aldehyde because the chlorine would leave, the hydrogen would come in because NH4.
Yeah, but oh, I'm missing something.
You keep baby.
What does come in into the aldehyde?
The NH4, the ammonia itself, will come in and then there will be a series of reactions,
Yeah.
and then you'll be left with probably just the aldehyde, which is how the chlorine leaves.
And the aldehyde, how does it react to the anhydride?
It's going to just break this bond, so you're going to get one side that's aldehyde, one side that's an ester. Ester. So like, see how this
One
is.
aldehyde and one ester.
Because it'll be aldehyde plus ester because this anhydride once it breaks.
If you don't mind me.
Yeah, sure.
So, like this portion over here is the same as this right here.
Right.
And how do you get the
So these are two different things. These are two different things. I'm saying like if you cut this here, you now have aldehyde.
they were both reacting.
No, that's true. Which one is more reactive than the other?
Oh yeah. Oh, the chlorine. Okay, yeah, makes sense. Yeah, never mind. I was looking at it. I'm trying to remember.
What would be hydrolyzed more slowly? Okay, so how this comes down is came out of one of the questions earlier on. But basically it worked out to where for the same reason that we just looked at this.
Yeah, the
Clean
CL
out.
is most reactive. It's the best thing for
Right, exactly, it's the same exact question.
Oh, I have a question about that. Would Tuscany would be more keen to? It will be a better group, living group than Halide.
Yes.
Yeah, right. Okay.
Okay, so, yeah, we just did that. Ensure knowledge of insurance to protect schools from these students who are very hurt. Okay, yeah, so this is just asking which set of reactions would actually go through. This, like, what it came down to, it's going, the reaction's going one way instead of being both ways. So like for this one, the reactants would have needed to be switched. Like trying to just pull these two things together.
Yeah, it's not possible.
Right. So that's pretty much what it came down to, all these answers being wrong or right versus this one. And then the same kind of question. This one, like, it's one of those when I was like, okay, if it looks not like what they already gave you, it's not the answer, it's because they start adding too many, like, there's too many products, or too many cartons on something, or there's something that's missing. So like, if we just took something like this, how I kind of hacked it up a little bit, we can see that there's things that were added or missing in the rest of the answers.
The other one that has just water is C, right?
Right.
Okay.
And then this question is still the same thing. It's like they started doing too much with everything, and it's just like we weren't asking for all that. We were just trying to replace the floor.
Sort of like a theory.
Right. It's just like a basic addition kind of thing.
Oh, okay. If there wasn't, if it was just carboxylic acid, no. Yeah, if you had a ketone, it would replace the oxygen, right? You would have like a.
Oh, yes.
Yeah.
Yes. See how they turned and rotated everything, and it wasn't supposed to be like that. So like how you have how the answer starts CH3, your carbonyl group, so they're both the same. The only thing that should have been replaced was your chlorine.
Yeah.
And then that's
if
all
the
they
chlorine
did.
was that's what I'm saying. If the chlorine was a carbon, then C would be the answer, right?
Still no, because they made a double bond to the
oxygen. So you have it will be an imine synthesis. You had like a ketone instead of chloride, right? I'm just
if you had an alcohol instead, that could have happened. Not if if you had a ketone, there was too many steps involved for like the simplicity of this kind of answer.
Oh. Okay.
See, like here it's just too many steps to get this double bond to form versus you just literally hack this off, hack the chlorine off and replaced it.
Okay.
Even here, they didn't need to
Yeah,
reduce it.
there's no hydrogen source anyways.
Right. So they're just adding things and it's just kind of
Yes. Yeah, I see how they make it.
yeah,
They
it's
just
just
put some ridiculous thing on every single answer except one of them.
right. So if you're like high stress and you're sitting there not like really reading the question, you can see like it's gonna be like simple mistakes.
Yeah.
So again, here this is still like one of those. All they're gonna do is
What's the question?
I really need to hear this. That's the big one.
Yeah.
So if you like hack this question up, since it already gave you the OH chemistry here, all you're gonna do is send this back up to the top of this one. So you have your OCH, your COCH right here,
Yeah.
and then the OH goes to the bottom. So it only needs B. Because it couldn't have been C because this is still closed. this was not, this one could have almost been answered, but they were missing the hydroxide.
Oh, they just took it away.
Right, and then they added stuff in this one. Yeah, and this comes back down to your more reactive stuff. And they had too many products, so it's kind of like, okay, it can't be anything except these two things because it starts, like you're going to start and finish with the same amount of carbons. When it's just like water being added to it.
Oh, and the anion is because it's like all like base, right?
Mhm.
You have a lot of base in it.
Right.
Yeah.
This section just continues on like that.
There's not much like amino acids or stuff like that. Like,
No.
from what I can see, right?
And it's not this kind of test.
I don't know.
It's that they make a biochem ACS, so that's why it's probably not here.
Oh.
There.
I don't know why they made me study it then. I guess in preparation for biochem. But I had a test this Monday just on amino acids for those sense if it wasn't going to be in the ACS.
Yeah, it's not. It's not. I think if you can go through and like see like exactly what we're doing, like each answer, why is this one right or wrong, then you'll be fine. Because if you understand, you'll have to go back and probably read through some of the chapters and figure out why it was right or wrong.
Yeah.
Like that material things, and that's what we. But
Yeah, I don't understand the degree.
that's my whole life, and I've never seen it again after this class. Okay.
OH, ODD,
Yeah, here it goes again. You might want to go figure out what it's about because this is the third time.
So if it was just right here, is that a benzene on the end? C6H5, yeah, right?
It could be, or it could just be. It could just be like a phenol or something.
Oh, okay. Or it could be just a linear.
Yeah.
Why would they do that though? Like if it's benzene, then the reaction is different.
Well, I think because they left it simplified here, or maybe they just didn't want you to see it that easily. But it is going to have. It would have to be a benzene. It fits the character.
What is the right answer? E.
B. Yeah.
C, D.
It was a alpha carbon replacement. So yeah, this would be our alpha carbon
Yeah.
in comparison to our carbon delivery. And that's where it replaces it. And yeah, only B and D had that, but D had all three turned into
It's only the alpha hydrogen that if you
Right.
switch that.
right. It was only that one. Huh, how could be the answers to the rest of these problems?
Yeah.
Something to do with the alpha hydrogen. It would be so that simple. Okay. Okay, so this is the reaction, and it's just moving through who knows what.
Oh, that's the weird reagent.
Mm-hmm.
So you have two R groups,
Mm-hmm.
lithium, is that it?
Mm-hmm.
So
So
if one of the R groups hits the O, right?
right. No, well, they both go one on both sides.
Yeah, the alpha part.
So that none of the carbon is bulky.
Okay. Right. These are